So I'm going to start the lecture. First, let me introduce myself. I am Andy. I'm working with Professor He. And last Wednesday, he got a kind of very serious fever. So he was not able to come last Wednesday. He canceled the course. For today, he have not recovered yet. So I'm going to lead the two lectures. One is what should be covered from last Wednesday is called the knife base, and then we will move to today's topic, the LDA model, and the LDA model will be your first assignment. So let's start. So before we talk about the LDA model, before we talk about the knife base, we need to get some background of the Bayesian, the Bayes theory, which is the most important formula in the probabilistic machine learning. So it is given by PA. This is given by the probability of A conditioned on B, and it equals to PB given by A times PA over the probability of B. So by this very simple and naive formula, we can have the two very super easy derivations. One is the joint distribution of the A and B. So it's given by PA given condition on B times PB. The other is vice versa. So we can set them to be equal and we can solve some of the problems. So if we apply the Bayes rules for the machine learning problems, it can allow us to reason from the evidence to the hypothesis. So another way of thinking the Bayes rule is to, so let's just replace the A and B with the hypothesis and the evidence. So in this case, the hypothesis given by the evidence equals to the probability of the evidence conditioned on the hypothesis times the probability of the hypothesis. And it is divided by the total probability of the evidence. So here we can say that if we are trying to run a machine learning model, then the evidence is some kind of training data we are doing, and the hypothesis is the final estimation we want to arrive at. So this term, the P hypothesis, is our kind of initial assumption over this data. We might assuming that we have a spam email classification, we might have a kind of a prior understanding. Maybe 50% of the emails should be categorized as a spam email, and the others should be the normal email. So that is a hypothesis. I mean, that is a prior assumption. And eventually, given by the training data, we can finally get this term, the hypothesis, conditioned on the evidence. So this is this is a kind of a formal definition. We have the pH, PD given by the H, pH conditioned on the D. So here H represents the hypothesis, and the pH is a prior probability. The Bayesian, if we want to apply the Bayes rule, then we want to reach the posterior probability of the H. So we use a kind of learning to finally get this posterior distribution. The whole learning scenario is by the P hypothesis by the data or by the evidence equals to this one. So this condition, this considers a set of the candidate hypothesis H from the model, and it also attempts to find the most probable one H from the whole hypothesis distribution. We use a term, the maximum posterior hypothesis, the MAP, to represent the best, the most probable hypothesis from this distribution, which is given by the argmax of the H from the final distribution. We just take the best one over the posterior hypothesis, that is the MAP. So another term of using the hypothesis is if we do not apply the Bayes theory, then we just use the maximum likelihood hypothesis, which means we do not have the original prior assumption of the data. We just run the experiment, and the final distribution from the experiment will give us what is the best way, what is the best hypothesis. So it just takes the argmax of the PD given by the H. Note that it is different from this term. So this is PD conditional on H times the prior, and this one is just the PD given by H. So let's just take one example. So we assume we have a corn that is either fair or have 60% of the time that is have a bias in favor of the head. So we want to decide what is the bias of the current corn. So it is kind of a learning problem. And if we have two hypotheses, one is that the probability for you to get the head is 50%, and the other hypothesis, the probability for you to get the head is 60%. And then if we have our initial assumption, because maybe we look at this corn and we find out the shape of this corn is different from the normal ones, so we know that it is more likely for it to, when we just drop it onto the ground, it's more likely for it to be the head. So we have the prior, and the prior is the pH1 means the probability for us to have the first assumption is 75%, and the probability for the second hypothesis to be true is just 0.25. So let's consider now we have the experiment, and we just run it one time, and from this one-time experiment, our result is that the corn toast is head. So in this case, we can have the D given by H1 is 0.5, and this one is 0.6. So based on this two, we can calculate the total probability of PD. Just sum the two scenarios together. So it equals to this one. So if we use the MAP or if we use a Bayes theory, we can get an updated version of the posterior. This posterior is given by the hypothesis of the H1 given by the current experiment is going to be 0.714. So for the other hypothesis to be true, that means for this one to be true, it is 0.286. So if we use the maximum likelihood, that is to say, if we do not use the Bayes theory, we just assume everything to be equal likely. There is no prior. Or the prior is just equal likely to be happen. Then the data actually supports the bias corn better. So in this case, actually, the Bayesian theory does not give us a tendency that it is more likely to be the head. So how can we do that? We just need to run this experiment more than one time. Maybe we can run it 100 times, and the experiment shows that 70% of the time it is head. So if we use the maximum likelihood, then the final hypothesis should be 70% for it to be the head. But if we use the Bayes theory, then it will be like this. So because each time we run the experiment, for the first hypothesis, it is 50% of the time to be head. The other 50% is a tail. So it follows a binomial distribution. So we use 0.5 to the degree of 50 times 0.5 to the degree of 50. Together, it will be 0.5 to the degree of 100. And it times with the probability of the hypothesis 1 plus the plus 0.6. Again, this is a binomial distribution times the probability for the hypothesis 2 to be true. So in this case, our PD will be this one. And given by this 100 experiment, we finally find out the updated posterior of the H1 conditional on D will be this value, and this will be very large. So if we use a Bayes theory, we can finally reach a very large value to say that this so this coin is actually biased towards the head. So is that is everyone clear with the several slides? Okay, cool. So in this example, we have to choose one hypothesis out of the two probabilities. Realistically, we could have infinite many to choose from actually, and so that is the MAP. We're coming back to the maximum likelihood estimation. The previous one is maximum posterior. This one is likelihood. It means you just run the experiment to get the hypothesis. So in this case, if we use the MLE, the maximum likelihood estimation, if we use this kind of binomial distribution to represent the current experiment, we will have the P probability for it to be had 1 minus P to be tail, and we run the experiment M times, we can get the distribution to be PD conditioned on P to be the binomial distribution. And to ease our calculation, we can choose to use the log likelihood given by the log likelihood of the P should be this one. And if we want to take the maximum, we just set the derivative of the current likelihood function to be 0. So we can get this one. And if we want to solve for the P, it will give us K over M. So that is the maximum likelihood estimation. So in practice, this example is just we were assuming the model is binomial, but in the real world case, it can be multi-monomial. It can be a lot of scenarios. It can also be some other distributions, and also we want to have the smoothings. We are going to talk about the smoothings later, because if you do not have the smoothing, sometimes you may have the value to be 0, and if you just use 0 for the probability in the calculation, then everything will be 0. So smoothings will be very useful. Okay, so now I'm going to talk about the naive Bayes. When is naive Bayes very useful? A very traditional scenario for the naive Bayes is to do the text classification. So we can use it to detect what is the spam emails. We can also use it for the sentiment analysis. We classify the current tweet data to be positive or negative or neutral. So this is a very we can also have the authorship attributions, the language detections, the news categorizations, and all the others. As long as it is a kind of a classification problem, we can use naive Bayes. So if we want to do the text classification, our input should be there's a document. There's also a set of the classes for us to choose from. So the classes can be positive, negative for the binary classification, and the output will be our prediction for the current class for the current document. And the conventional way to do the text classification is to use a rule-based, which means we just design some specific rules. As long as the current document contains some words like good, great, extraordinary, then we will mark this document as positive. However, this kind of rule-based classification will definitely have some drawbacks. Though it can be very accurate, but the rules will be very hard to define. And sometimes it can be unknown to us. We never know how we actually decide this is a positive, like a positive tweet, whether this is negative. We just feel like, okay, maybe the current tweet is giving me a kind of attitude, this is positive. So some of these rules might be very hard to define. And also, if we want to include other words for the rule-based classification, it will be very expensive. And also it is not easily generalizable. So we might need a kind of supervised learning model to deal with this kind of scenario. So we have the naive Bayes, the logistic regression, the support vector machines, and also the K-and list labels for the classifiers. And today, for the multinomial naive Bayes, what we do is, again, we're applying the Bayes rule. We have the C, the class of the current document. The D is a document. So the naive Bayes can be written in the Bayes rule, and if we want to find the MAP, that means we want to do the argmax of C given by this probability. And we need to have two terms. One is the prior probability of the current document class PC, and the other one is PD given by the C, the conditional probability of generating document D from the class C. So how can we calculate these two terms? There are two options. One is we just represent the entire sequence. That means represent the entire document as a sequence of the words, the P, W1, W2, W2, WK conditioned on the C. But there are a lot of sequences, and also in this case, we do not know like whether the words have the the time series information, whether the current word actually depends on the previous word. So this is pretty hard to represent. So the other option is we can represent the current document using the back of the words, which means we are assuming each of the position for the word is actually irrelevant. So the current word can appear in any of the places in this document. So in this case, if we assume other words to be independent, we can represent this probability to be just the multiplication of other words conditioned on the class. So that is what we are going to do if we use the backup words to represent the PD condition on C. So the backup word is like if we have the documents and we just take a back, we do a counting of how frequently the current word appear in this bag. So for example, in this document, we find out it appears 6 times and I appears 5 times. So it's just a kind of dictionary containing the number of the words the number of appearance for the current word. So this is the backup words. So now we have the MAP given by the argmax of the PD condition on C times PC, and we can represent the PD condition on C to be word 1, word 2 to word K condition on C, and because we are assuming they are independent variables, so we can take the multiplication of the words condition on C, and I mean using the backup word assumption. So this is our current formula for the naive Bayes. And then the whole procedure can be represented this way. We first find out word 1 condition on C, and then we find out the other words. And each of the words will have a class information, and the whole document is represented by the left side. So this is for the document 1. For the document 2, this is we just apply this procedure again, and we can generate the entire data set one document at a time. So previously, I just discussed how to calculate the PD condition on C. Now we need to decide how can we do the PC and also the P word condition on the C. So an easy way to represent it is to use the maximum likelihood estimation. That is to say, if we are given the training data, we just need to do a counting of how many classes of the current data it is. So if we have 100 documents and 40% of the document is positive, then we can say that the PC, the prior is 40% for the class to be positive, and to be negative it is 60%. For the words, again, we just do a counting. So we will look at the current document and look at what is the current word, and we do a counting of the word together with its current category. If we do this counting and we normalize it with the counting of all the words by the current document, so we can find the probability for each of the single word conditioned on the current class. So that is how we represent the PC and also the P word condition on C. So given by these two formulas, with the maximum likelihood estimation, finally we can take we can take this one to get our naive Bayes. In some, but in the real case, we have the data sparsity, which means we might need to, when we are doing the counting, we can find the amazing for the positive attitude. Actually, if we do the counting, it just appears 0 times. So it means the probability of the amazing condition on the positive is 0. In this case, as long as we have one term to be 0, then we take the multiplication of other probabilities, everything will be 0. So the final estimation will also be 0. So how can we deal with this problem? Do anyone want to like what? Still, I mean, if you take the log, it's the log of the 0 will be, it does not occur. I mean, log cannot take the 0. So that is how that is why we need to introduce the smoothing. What does it mean to be smoothing? If we have some of the 0 terms, we just need to add some very small values, alpha. Maybe the alpha here can be 0.01, 0.00001. As long as it is larger than 0, then using this Laplacian smoothing, the probability will no longer be 0, and it will be helpful for us to calculate. So I also want to ask a question here. If the alpha here is very large, what will happen? Do anyone have some thoughts?
What is the the denominator?
Oh, this one?
Yeah.
This one is the vocabulary, the vocabulary size.
What is the vocabulary size?
Vocabulary size is like, yeah, the number of words.
So I mean, number for so like a number for pieces or number for words.
The number of words. The W, the number of words. So what if the alpha is very large? What will happen? Yeah, so if the alpha is very large, then we can say if it is infinity, then we can just ignore these two terms. We just need to consider this one. So yes. So that is a problem. Yeah. So we need to have, so alpha is a kind of a hyperparameter. We might need to like tune it several times until we find out the best alpha for us to choose condition using for this training data. I mean, so this is when we need to do the smoothing because we need to resolve the problem that in some cases the probability of the counting will be 0. So that is a whole procedure for us to do the naive Bayes. The input will be a set of the annotated documents, and we compute the vocabulary V of other words. We calculate, we do the counting, and we calculate the probability for the classes. And we also do the counting to calculate the probability for the word condition on the classes. And then we can do the prediction for the document. For the whole document, we just need to use the MATP, the maximum posterior, to estimate what should be the probability for the current whole document to be positive or negative. Yeah, it's very naive. Because the naive Bayes will assume every word in the document will be mutually independent from each other. So this is very easy. Just do the countings and then do the predictions. There is actually, I would say there's actually no like training procedures for the naive Bayes. So that is naive Bayes, and we can use the naive Bayes as a language model. We can assign the class. We can use the model, and we can define what is the probability for it to be positive or negative. And for each of the sentence, we can have the value for each of where we can decide what should be the probability for it to be positive, negative, or both equal. It's just the example here. So in general, okay. So in general, the naive Bayes can use a set of the features, not just the words. We can also include some other linguistic features like the POS taggings, the label of the word, whether the word is a noun phrase, is a verb phrase, or the others. We can also include some others like the URLs, the email addresses, the capitalizations. We can have the domain knowledges. Again, this is just the rule-based features. So we can include as much as possible, as long as it can be calculated. It can be calculated by the naive Bayes. And if we want to evaluate our current classifier, we want to evaluate naive Bayes, we use the precision and the record. So the precision is the selected classes that is correct, which is given by the true positive over true positive plus the false positive. As a record is the percentage of the correct items that is selected. So record equals to true positive over true positive plus false negative. And this table represents the predicted conditions and also the actual conditions. The predicted conditions is by the model. The actual conditions is the real ground truth values for the current document. And the true positive is like the overlap between the predicted condition of the positive and also this positive to be true positive. And this one is false negative, which is overlap between the negative by the condition by the prediction and also the actual condition to be positive. This is false positive. This is true negative. So we use the precision and the record to evaluate the classifier instead of just using the accuracy, because in some of the cases the accuracy might be biased to do the evaluation. And if we combine the precision and not together with the record, we can get the F1 score. So the harmonic mean of the precision and the record is like we use 2 times precision times record over precision plus record. Okay, there is some problem for the display. Or in general, we can have some of the hyperparameters to represent the F score. We can use the beta here. 1 plus beta squared times the precision times the record over beta squared times precision plus record. If we want to if we want to find some other versions of the F1s, F scores. So now we talk about the advantages of naive Bayes. It is very fast, low storage requirements. It's very robust to the irrelevant features as well. It is also very good in the domains with many equally important features, and it is optimal if the independence assumption holds. So, but in some cases, we may have the variables in the current data set that is dependent with each other. For example, if we want to classify, let's consider a kind of example. If we want to classify, let's say if we want to classify some of the data set and the variables are like whether the current person is female or male, whether he or she have a higher weight or lower weight, and the weight and the gender may have some kind of relationships within. So there, if there existing some of the relationship of the variables, then maybe using naive Bayes will not be an optimal choice. But still, it will be a very good baseline if we want to do the text classification. And there are also some of the failure cases of naive Bayes. So, for example, in the XOR problem, the naive Bayes cannot learn a decision boundary because both of the variables are jointly required for you to predict the classes. You cannot just decide the results by each single value, and also the XOR means that we need to consider the two values together instead of assuming that they're independent. So the naive Bayes definitely cannot learn this XOR. There are also some other failing cases. For example, the class imbalance. One or more classes have more instance than the other than the others in the data. And in some cases, data may show the data screw will cause naive Bayes to prefer one class over the others. So the potential solution for this case will be the complement naive Bayes, but I'm not going to like introduce more details of that. It's just a potential solution. So the second part of today's lecture is the LDA model. Just a recap of the naive Bayes. The naive Bayes is also called a mixture of the unigrams. So if we have the model for each of the document, we can choose a topic we call it ZD with probability the P topic for the current document to be theta, and we want to choose n words Wm by drawing each one to be independent from a multinomial condition on the ZD with this probability, and it equals to the beta. So by saying the multinomial, I mean we can just take a non-uniform prior dice with a word on each of the side, and we just roll the dice n times, and we count how often each word comes up. So that is multinomial distribution. And also, there is a kind of a very strict assumption of the naive Bayes. That is to say, we can only have one topic for the current document when we are running the text classifications. So how to solve that? A potential solution is to use the LDA model, which assume which assume each of the document is a mixture of the topics. A single document may have 10 topics within itself. So it's different from the naive Bayes. And so now what we do is for each of the single document, we can first choose a multinomial distribution theta D over the topics for the current document. And then for each of the word within this document, we can choose a topic Zn that represent the topic that represent the distribution for the current word, and we have the probability for the topic for the whole document. Then we choose a word Wm from the multinomial condition on the Zn with this probability. This is very similar to previous slide. And then the topic will have a different probability of generating each of the word. Yeah. So before we move into the LDA, I first need to talk about the conjugate distributions. Because there are some specific, there are some terms in the LDA might be very confusing for the learners. So let's first look at the base rule. If we have the prior is the PC here, and the posterior is this one. If we have an experiment, we want to run the experiment several times, and we want to update the posterior. So that means if after we run the experiment the first time, we can get the posterior, then we can use the posterior of the first experiment as the prior for the second experiment. So if we want to do this, then we need to make sure that the posterior will have the same distribution, and will have the same distribution as the prior distribution. So that is in this case, we can say that there might be some relationship between this term, and also this term. So we need to introduce a conjugate distribution here in order to make the posterior to have the same form as the conjugate prior distribution, which also it calls the closed form. Just to so it can help us to ease the calculation. So there are a lot of very hard mathematics on this slide, but you guys do not need to really remember that. I just show some of the things to make the explanation to be more easy to understand. So I will need to use a gamma function. The gamma function is just a function that takes a random variable, and the final result of the gamma is just gamma with n equals to n minus 1. And also, and we can also have the beta distribution. So the beta distribution is calculated by the gamma. And one interesting fact of the beta distribution is that by this deduction, we finally find out if we want to draw a random variable from the beta distribution, then the mean of this current variable actually equals to this one, alpha over alpha plus beta. So why the beta, why we need to use the beta distribution here, and why we need to use the gamma function here, that is because actually the beta is a conjugate of the binomial. So why that? Let's assume let's assume a very simple case. We have the likelihood function to be the binomial. We can also have the prior distribution to be the beta. So so in this case, we can just so this is beta, and this is the likelihood function is the binomial distribution, and we want to find the posterior. The posterior can be represented by this. So if we just multiply them together, and we can find out actually eventually we can reach out the posterior to be in this form. So the posterior again actually is still a beta function. So because of this kind of a special relationship between the beta and also the binomial distribution, we can use the beta to ease the way for the calculation. So if we want to extend the binomial to be multinomial, so the multinomial will have a formula like this. We have k random variables in our current setting, and we also have the probability for each of the variable. Then the probability to draw this kind of multinomial distribution will look like this. So the conjugate of the multinomial distribution will be the Dirichlet distribution. It is given by the formula with the b of the alpha times the multiplication of the x to the degree of alpha to the degree of I minus 1, and the beta of the alpha is like this. The beta, the beta, the alpha here is just a hyperparameter. I'm going to discuss some of the interesting fact of the alpha later. But so the mean of the variable, if we want to draw a mean of the variable from this distribution, it will give us this. So because the so if we are using the LDA model, then we need to have the multinomial distribution. Then if we want to have a very easy calculation, we need to have our prior to be the Dirichlet distribution. So in this case, because the prior is Dirichlet distribution, and also we are drawing the multinomial distribution, then our final posterior will also be a Dirichlet distribution. Another way of writing the Dirichlet distribution is like this. So it is actually defined over k minus 1 simplex, which means it takes a k non-negative arguments, and the sum of them will be 1. And it is another attribute, as I said, is a conjugate prior to the multinomial distribution. So if our likelihood is multinomial with this prior, then the posterior will also follow the same distribution. So the alpha here can be kind of a prior counting of the ice class. Another way of understanding the alpha here is So if we have the Gaussian distribution, there's a hyperparameter C for us to control how the standard deviation look like for the Gaussian, and the alpha is doing the similar things. And for the LDA model, we often use symmetric Dirichlet where all the alphas are equal. So the alpha is then the concentration parameter. Okay, this slide is just repeat what I just mentioned. So by saying the concentration, I mean if the alpha is smaller than 1, then the majority of the probability mass will actually be in the corners of the simplex. So this is a visualization of when the alpha is smaller than 1. In other cases, if alpha is larger than 1, then most of the document will contain words from most of the topics. That means it will have more diversities. So the whole LDA model will look like this. We can go from the top to the bottom. We first have the alpha. Given by the alpha, we can draw theta to be the topic distribution. Then for each of the word Wn, we can choose Z. Z follows a multinomial distribution conditioned by the theta parameter. So this Z will represent the distribution, the topic distribution for each of the single word. And then we can choose a specific word, and this word will follow the multinomial distribution by the beta, and each of the topic will have a different parameter vector beta for of the words. So the whole LDA model is like we first have the alpha, and based on the alpha, we can have the priors, and we can generate the theta. And with the theta, we can get we can just random sample a Z, and Z will represent each of the word within the single document. Then we introduce the beta together with the Z. We can get each of the word. We can get the distribution of the word. So that is for the single document. And finally, we have the M for the whole for all the documents within the training data set. The full formula for the LDA model, the parameter estimation for the LDA model look like is given by these two formulas. So we can take it step by step. So the theta is like this is not showing. Okay, so the theta is the topic distribution for the whole document, and the Z is the topic for each of the word within document. So initially we will have the Zn conditioned on the theta, and we can times it with the probability of each of the word conditioned on the distribution for the topic condition for the word together with the beta, and we do a summation of the distribution for the word. We can get the whole distribution, and we just so now now we can have the each of the word, we can get the distributions. Then we just times them together. We can get we can get the topic distribution for the whole document. So this part is get the topic distribution for the whole document, and then we can we have the theta for each of the document, and then do an integration over the document. We can finally get the words condition. Each of the single word for the whole data set condition on the alpha and the beta. Is my explanation clear? Okay. So for the formula here, still again we can look at from this one. It's actually it's very similar. So this is from here, and this is from here. We just so actually there's no difference. This is just to say that this is the current. The D is the like the current document for the distribution. We just add the D here to know that there's different betas for there's okay. So how can we do the training? Because LDA model is kind of unsupervised learning. There's a way for the unsupervised learning that is called the expectation maximization. That is to say, first we can find out what is a z, what is a theta. Then we can, so that is called the E step, the expectation. Then we use the maximization to update the parameters for the expectation. So if we run it multiple times, it's like we first project everything to be the latent, and then the maximization will convert, will project the latent to be the final distribution. And based on the final distribution, we can draw estimate and then run. So that is one iteration. If we run a lot of iterations, then we can get the updates of the parameters for the current model. So that is called the expectation maximization, and it contains the hidden variable, the h. In this case, the hidden variable is the z and the theta, and our goal is to estimate the v in the unlabeled data. So we need to write a function that bounds the maximum likelihood estimation. And we also have the alternative steps that will increase this maximum likelihood. The E step is given the V, we feed the function Q of the hidden variable condition of the X and the V that approximate this distribution. And in the M, we want to do the maximum likelihood estimate of the V for the Q. It's just it's like the reconstruction as a distribution over the missing variable for the H for the hidden variable. So the whole procedure is like we first for the E step we will compute the P, theta, and the Z conditioned on the vocabulary each of the word, and also the W and the beta, which is the posterior of the hidden variable theta and the Z. That is, and in the M step, we estimate the parameters, the alpha, the beta, given the current hidden variable distribution from this one. And the problem with this is that the E step cannot be solved in a kind of a closed form. So some people will say we can use a variational approximation. So in the variational inference, we consider simplify the graphic model with the variational parameter, the gamma and the psi, and to minimize the KL divergence between the variational and the posterior distributions. So that because the P and the Q will be different, but if we use the KL divergence, we can shorten the distance between these two distributions, and then we can say that actually the Q will be as similar as P, so that the whole EM step will be useful, will be like a kind of simulation for the correct the distribution estimation.
So what would be the original distribution? So you need some variation distribution.
Yeah.
Which one? So variations.
Do you mean the KL divergence?
Yeah, no, KL divergence.
Yeah.
You propose distribution.
Right. Oh, so in this setting we are using multinomial distribution, or we can use the Dirichlet distribution. I mean, in the intermediate part for the KL. Yeah. So that is a variational. I mean, that is a variational posterior distribution for the for the LDA model. So given the corpus of the document, we can find the parameters, the alpha and also the beta. We want to maximize the likelihood of the observer data, that is the training data. The E steps is this one. And it's so for today, it's just a brief introduction of the LDA, because it is too complicated. So you do not really need to know a lot of details of that. We have the hidden, and also we have the observed variables, and that is what the EM algorithm and why EM algorithm will be working here. The other version of the LDA is to have the smooth LDA. So by saying the smooth LDA, we just have some kind of hyperparameters to do the smoothing. That is a single scalar parameter that is larger than the 0. So we can include this kind of smoothing variable like here. So by this kind of smoothing, in some of the cases, it can like have a better performance than the conventional LDA model. Different from the original versions, now in this case, because we have the smoothings, then for each of the topic, we can draw a multinomial distribution of the word. And in this case, due to the smoothing, our beta now counts with the distribution by this eta. And for each of the document, now we first draw the multinomial of the topics by the alpha, and for each of the word, we will draw the topic for the distribution for the words from the theta with this one, and we draw the distribution of each we draw the word from the multinomial distribution by the beta, because the beta is changed. So this is the difference between the smooth LDA and the previous conventional LDA. It's let's see some of the examples of the LDA model. Let's say, so the art, budgets, children, education is the topics of the current LDA model. By the LDA model, it can find some of the words that represent the current topic. So for example, the arts will have this list of the words representing arts. The budgets will have this list. The children will have children, women, people, child, years, families, work, parents, and the others. For the education, we have the schools, the students, the education teachers, or the others. So this is like for each. So if we have if we set the hyperparameter to ask the LDA to find 4 topics. And we want to maybe we want to find the top words for the current topic, then this is what the LDA model will give us. So this, how did it select the words? The words means that it appears with the highest probability over the whole distribution for the current topic. So the LDA model will select this word to represent the current topic. And if we put the distribution, if we put the distribution by the LDA model onto the current document, we can have a visualization of the topic like this. So the words with the same color will be estimated as the same topic from the LDA model. This is how the LDA model work on the documents. And the interesting fact is that the LDA actually requires fewer topics than the knife Bayes. This is a comparison. We can find that if we have the smooth mixture unigram, this is like so the number of topics is like this with a perplexity. But if we use the LDA model, or if we if we use the LDA, if we use the topic models, we will have this one. If the this result shows that the LDA model will have a lower perplexity and will have a better performance. there could also be some extensions of the LDA, like the LDA can be embedded in more complicated models for the intuition of the structure of the text, because it can because it can select what is topics of the current document. It can also assign each of the words with a probability for the current topic. So after we get the LDA information, we can do a kind of a parsing for the current document to visualize how the structure of the document is. So this is one extension of the LDA. It can be used in models that count of the syntax, also the authorship, the word sense, the dynamics, the correlation, the hierarchies, and also the other structures. However, there is some problems with the LDA. For example, in the LDA, we only consider the words and the word frequencies, and some of the words may appear together. So LDA will have the n-grams, maybe just 1 gram. So it consider 1 word, 2 words, 3 words that occurs together. They consider they have some relations. However, they do not include the semantic information. It just considers the syntax of the words. So this is a problem with the LDA model. It's just consider the unigrams. It does not have the it cannot consider the structure of the sentence. It cannot consider how the word means in the current sentence, whether the word have a different meaning for the current document or for the other document. This is a problem with the LDA model. So to give a summary, today we learned what is the knife Bayes, what is Bayesian learning, the maximum posterior, that is to take the argmax of the hypothesis, the distribution of the hypothesis after we get the P hypothesis conditioned on the training data. And the maximum likelihood estimation is just to use the data conditioned on the hypothesis. That means just to do the experiment to find out what is the best one. And the knife-based model is we have the words conditionally independent from each other given the class, and also we take the maximum likelihood estimation. That is to say, we do the counting of the classes and also the words to find out what is the probability for the class, what is the probability of the word conditioned on class to run the knife Bayes. And during the inference, how can we do how can we find out the document condition on class? That is just to do the multiplication of each of the word condition on class, then we can get the documents. So the formula for the knife Bayes is this one. That is for the knife Bayes. And for the LDA model, so the LDA model will assign the topics for each of the documents, and each of the topic will be represented by the words. Each of the word, so the LDA will have the distribution, will have the probability distribution of the words for this current topic, and for the whole document, it will also have a probability for the document to be assigned with some of the topics. So that is the LDA model. Each of the topic is a distribution of the words, and each of the documents is a mixture of the corpus-wide topics, and each of the word will be drawn from one of those topics. Yeah, so that's everything for today. Do anyone have questions over the previous slides or something else? Okay, so class is over.